Today we're going to start chapter 11, which is all about multiple linear regression. So today we're going to start section 11.1, and we'll use the date of April 27th. The learning objectives in this section are to examine our multiple regression model for the population and how to set up our own multiple linear regression model, as well as use it to make predictions. We're going to look at how we collect data in multiple linear regression. We're going to design confidence intervals and run significance tests and look at the variation and our correlation value of R squared. So in chapter 10, we examined simple linear regression. And basically what that said was we were looking at the response based on one explanatory variable X. And this is the model that we used for simple linear regression. Beta 0 was our intercept. Beta 1 was our slope. We would sub in for our X value, and it would make a prediction for the mean response Y. But in reality, it's not just one variable having an effect on the response. So it could be that there's something else needed in our model to make it more accurate. When we look at explanatory variables, we know that there could be lurking variables playing a role. So most oftentimes in multiple regression, we will examine multiple variables and how they're all affecting the prediction of the response variable. So what we're going to do is use P explanatory variables, and the value of P can change. It could mean 2 variables, it could be 10 variables. It just depends on what the problem presents. But our variables will be labeled X sub 1, X sub 2, and so on until we've exhausted the number of variables in the model. And then it does give us a brand new model that looks like this. So we'll still have the mean response, and we are still trying to predict that. We'll have our intercept, but now you can see we have beta 1 with variable 1, and beta 2 with variable 2, and so on until we've gotten through all of the variables. Each variable will be related to its own type of slope. So when we gather our data for a simple linear regression problem, typically we have n observations. And remember, once we hit 25, that's usually significant enough. But it's 2 variables. We have an observed X and an observed response Y. But when we work with multiple linear regression, we'll still have a response variable Y, but we will have P explanatory variables associated with each of n cases. So maybe we're trying to predict your height, which is Y, but maybe what plays into it is X sub 1, which is your age, and X sub 2, which is your gender, and X sub 3, which is your foot size, and maybe X sub 4, the number of siblings you have. So the variables can be representative of really anything, but all 4 of these might be playing a role in predicting your height. Because there's so much information, typically we organize everything in the form of a table or a spreadsheet. So something to this effect. We would have case number 1, so maybe this represents Justin, and we're gathering data on his weight, his age, his shoe size, the size of his hand, the number of years he's gone to school, and so on, ultimately to get a prediction for his height at Y. When you look at the subscripts though, the first value is case 1, and the second value is variable 1. And then as you move on, it's case 1, variable 2, and so on. So maybe the next case refers to Lily, and we're going to gather the same information on Lily to make a prediction on her height, but then this would be case number 2, variable 1, and then case number 2, variable 2. And we would do this for all of our cases until everybody's listed in the table. Of course, we'll do this in our iPad so that we can run our statistical information. If you remember from chapter 10, we associated our linear regression with this format where data equals fit plus residual. So the statistical model for multiple linear regression is as follows. In this model, what we're seeing are lowercase b's. These would be obtained from our sample. Beta would represent our population as a whole. And the value of I represents any number of observations that we have. The fit portion combines the intercept and the slope and the value that each individual observation takes. And we know that the residual will be represented by E sub I. Remember, the residuals themselves should be independent and normally distributed. We don't know the standard deviation, so we'll have to use our sample standard deviation. And the residuals are present in the model, even though we're not going to physically write it down or use it in a calculation. So the parameters of the model to represent an inference are the betas, and then we'll use our sample standard deviation. We're still looking for the mean response of Y, and it's based on what we observe in our data. So when we gather our information, we'll calculate all of our beta values, but in reality, we're trying to infer this on the population as a whole. So the values of beta will be estimated by our lowercase b's from our sample. Now, typically we don't examine all of the beta values at one time. We will focus on one beta at a time, and the problem will usually state which beta value they want you to examine. So basically, if you're trying to interpret it and you're looking to see if the slope is 0, they're saying that when you change the variable, let's say x sub I, by 1 unit, you're holding the other units in constant. So we're only examining one at a time. Everybody else stays the same. When we graph all of our information, if it was simple linear regression, we would plot our x value and our y value. We would create a scatter plot, and then we would put in the least squares regression line, and that would be an estimator for our coefficients of beta. When you use the least squared regression line, it's trying to minimize the deviations that are occurring. So it's trying to place that line with little variation as possible. So this is what we'll see when we create our own regression line on the iPad. And as always, B sub 0 will be our intercept. We don't typically run any kind of inference test on the intercept. It would really have no value. So since we're collecting multiple variables, what's going to happen is when the line is created, it's going to show us how those each uniquely play a role in the prediction value of Y. The statement is saying they're analogous to the slope in simple regression. That's true. The betas or the lowercase b's that we'll see for each of our individual variables will represent the slope for that particular variable. Now we won't know standard deviation, so we also won't know variance. So what we'll use is S squared, which is variance, to measure the variability of the responses about the population mean. That tells me how much error is present in my model, how much of it is due to me placing the line where it is. This is the formal equation to calculate the variance. So again, it would be the sum of the residuals, and they're using observed minus predicted squared. You'll notice in the denominator, this is really going to be our degrees of freedom. N is our sample size, minus P variables. So if you collected 4 different pieces of data, it'd be minus 4. and then minus 1. When we set up our confidence intervals, we're going to use the values that are present to represent our parameters beta 0. They're using beta sub j. That just means that it could represent any one of the slopes present in your regression line. And again, we're going to use a t distribution because we don't know standard deviation. And our degrees of freedom, again, is represented by n minus p minus 1. On your formula card, this degrees of freedom formula is represented there, along with the model for multiple linear regression. And here's how we'll set up our confidence interval. It'll be represented as beta sub j. So this could be any of the slopes that are present. So we'll focus on that one. We'll have to select our critical t value, and then we want to use the standard error that goes with that particular slope. From there, we typically will run our significance test. So the null hypothesis says the slope of interest is equal to 0. We can run a one-sided or a two-sided alternative, but we're going to use a t statistic to calculate our value. So it'll be the value of the slope divided by the standard error for that particular slope. We'll want to incorporate our degrees of freedom. And in the picture, we can see that it could be one-sided. So beta might be greater than 0. It might be less than 0. Or if you're unsure, we can always run the two-tailed test. Don't forget to multiply your p-value by 2 in the end. And we'll continue to use our iPad or our calculator to calculate p. So at this point, we're going to put up our homework. So we're going to do 11.7 and 11.8. For 11.7, you're going to find a 95% confidence interval for each of the 4 different problems. And then in 11.8, you're going to run the significance test for each of these as well. And they do provide the standard error, so you don't have to calculate anything specific. If you have any questions, please make sure you contact me. And we have our regular Zoom meeting set up for Wednesday, question and answer. And then this Friday, we'll go over our homework. Have a great day.